When we have mixture of gases, then the molecules are going to behave independently, and each one is going to have pressure. The volume and the temperature, because it's in the same container, the volume and the temperature is going to be the same for different gases or component of the mixture, but the pressure applied by each gas is going to be different based on the number of moles of that gas. And this pressure is called like partial pressure. Partial pressure, it's based on each of the component of the mixture, each gas, and the total is going to be total pressure. If you add them all together, it's going to called total pressure. So if you have you have the gases of A and B mixed together, pressure of A is related to number of moles of A, pressure of the B is going to be related to number of moles of B. The total pressure is going to be total of the pressure A and pressure B, or instead of using one of the number of moles for one of the gases, you would use the total number of moles for all gases, or both A and B. So if we use this example, we want to practice this and get the okay. We want to find the partial pressure of the neon in a mixture with the in a mixture is basically mixed with xenon. The total pressure is 3.9, and the other information that is given. The total pressure is 3.9, and we have volume is 8.7, temperature and the moles of xenon is given to us. So if you want to find the partial pressure from neon, we have the total pressure. Pressure minus the pressure coming from xenon is going to give us pressure for neon. So all we have to do, find the pressure that is coming from xenon. The pressure from the xenon is going to be moles of xenon, RTB. We have to make sure that the units that are used in this equation, because we are using ideal gas law, the pressure is in ATM, volume would be liter, temperature in Kelvin, and the universal constant R is 0.08206. You can use that. So we find the partial pressure for xenon to be 0.9 atmosphere using the number of moles of xenon given in the problem. And if we have the pressure from xenon and we have total pressure, the difference is going to give us pressure for neon. Pressure for neon plus pressure for xenon is total pressure. If we have the total pressure, we can also find the mole. We can also find the partial pressure. Because the total pressure is coming from the total number of moles, and partial pressure from the each number of moles for each gas. So if we calculate the mole fraction, so basically partial pressure is fraction of total pressure, and the partial number of mole is a fraction of the total number of moles. So if we have that fraction of the number of moles, which is called mole fraction, and we calculate from the number of moles of A divided by total moles, or total number of moles, partial pressure then is going to be mole fraction times total pressure, because partial pressure is a fraction of the total pressure. And what is that fraction? That fraction is basically is called the mole fraction and can be calculated. So if you calculate the mole fraction, you have the total pressure, you can find the partial pressure. On the next example, we want to find the mole fraction and the partial pressure for mixture of three different gases. We have helium, oxygen, and we have helium, oxygen, and I think there's another one, oxygen, helium. To find the mole fraction is the mole of gas A divided by the total number of moles. And if we have the total number of moles, we can find the total pressure. So let's take just one step at a time. We are going to find the total pressure, find the total number of moles, and then find the mole fraction. In order to find the partial pressure, we say partial pressure for A is going to be mole fraction of A times the total pressure. So what we are going to do first, let's say we want to find the mole fraction for helium. The mole fraction for helium is the moles of helium. How do you find moles of helium? If the mass of the helium is given to us, mass of helium divided by molar mass of helium, that gives you the moles of helium. So we have the moles of helium, and that's going to be 24.2 divided by 4. So moles of helium, so N helium equals mass of helium, which is 24.2 gram, divided by 4 gram per mole. So that gives us 6.05 mole of helium. So as long as you know how the number of mole is calculated for each one. So we have the moles of, for mole fraction of the helium, we have the moles of helium and divide by total number of moles, which is moles of helium plus moles of oxygen. So we have mixture of two gases, moles of helium and moles of oxygen. The moles of oxygen, 4.32 gram, divide by 32, that gives the moles of oxygen, and that's where we're getting this number for the moles of oxygen. So we have the mole fraction for helium, which is 0.9781. If you add the mole fractions for two gases, it adds up to basically it adds up to 1. You can find the mole fraction of the O2 by subtraction. 1 minus this number, that gives you the mole fraction for the oxygen. Or you can do, for mole fraction of oxygen, you say 0.135, divide by this total. So you can get either way. You can get the mole fraction for oxygen separately, which is the mole fraction for oxygen, just that value is 0.02 here. Okay? 0.02. That's the mole fraction of oxygen. Now, to find the blue color is showing how to find the number of moles. Okay, and then mole fraction for oxygen is the number of moles of oxygen divided by total number of moles. Mole fraction for helium is the moles of helium divided by total number of moles. So we have the mole fraction for helium, and we have the mole fraction for oxygen. Now, the total pressure is going to be P total. It's the number of moles, total number of moles. So if we have the moles of helium and you add the moles of oxygen together, that would be total number of moles, which is 6.1 6.15 6.185, sorry, 6.185, the total number of moles. That would give you the total pressure. The total pressure is 12.099. This is the total pressure. And if you want to get the partial pressure for the oxygen, partial pressure for oxygen is going to be partial pressure for oxygen is the mole fraction of oxygen times total pressure. Partial pressure for helium is going to be mole fraction of helium, which is this one, times the total pressure. So we find the pressure coming from helium as 11.8 and the pressure coming from the oxygen 2.64. If you notice that it's kind of related to the number of moles, not just the mass, even though in this case the mass of helium is also greater than the mass of the oxygen. So number of moles of helium is greater, so the partial pressure for helium is greater than the partial pressure of the oxygen. Okay. The next topic is like collecting gases. When you collect gas over water, basically you are mixing the gas with water vapor. So it needs to be treated like a mixture. One would be the pressure coming from the gas. The other one would be the pressure coming from the water vapor. So if you look at this diagram here, how the gas is collected in a tube, and because the gas is collected over the water, some of the water molecules going to vaporize, go to the vapor phase, and also contribute to the pressure. The higher the temperature of the water, the higher the rate of evaporation water molecule and greater contribution of the water molecule. So if you look at the table here, it gives us the pressure that is coming from water at different temperature. So in order to find out how much pressure is coming from water, we have to refer to this table, or the problem would give that number. And based on the temperature, we pick the pressure that is contributed from the water vapor. So if you look at this question, is asking 1.02 liter of oxygen collected over water at 293 Kelvin with a total pressure of 755. Find the mass of O2. So if we want to find the mass of O2, we want to find out the other variables or enough data in order to use the gas law. And from the gas law, we find the number of moles of the gas. So in order to find the number of moles, we do need temperature. With the universal gas constant is given. We need the volume and we need the pressure. Volume is already given in this problem. The pressure, the total pressure is given. So what we need to do, we need to find that value of the water pressure or pressure coming from water vapor at that temperature, which is the 293 temperature. Because the table was given in degrees Celsius, we need to subtract to 73. At the 20 degrees Celsius is going to be 17.55 millimeter mercury. and we subtract that from 755, we have the pressure for O2. So we have the pressure for O2. Because is in expressed in, so it's going to be 737 after you subtracted 0.65, and this number is millimeter mercury. It has to change to ATM because for the ideal gas law, we must have the pressure in ATM. So we change that to ATM by dividing by 760. So we have the ATM. So N equals N equals PV over RT, and that equals to pressure, which is a 0.97059 ATM times V, which is 1.02, divide by 0.0821 times 293 times 293. So we have that, we have the value for N. The value for N would be calculated as 0.04 equals to 0.0411. This is the mole of O2. If we have the moles of O2, we can simply change that to mass of O2 because the question is asking for mass of O2. So moles of O2 times, that's, I'm just going to put this like blue box here, the moles of O2 times molar mass of O2, which is 32 gram over 1 mole, that gives 1.32 gram of O2. So this was basically the next topic, which is one of the application of the partial pressure. So 0.12 moles of another example of hydrogen is collected over water. The temperature is given, and we want to find the total pressure. So pressure that is coming from hydrogen, we can calculate that. So we are going to use the PV equals nRT. So this P pressure basically is going to come from the H2. So we are using the N of the H, also hydrogen. So pressure from the from H2 equals pressure from E2, pressure from the H2 equals N of H2 RT over V. Now, see what we have here. We have the N already, so that pressure of H2 equals 0.12 times 0.0821 times temperature is 323 over volume, which is 10.0 liter. So finding the pressure from the H2 is simple because we already know the ideal gas law, but finding the total pressure, which is the P total, equals pressure coming from H2 plus the pressure that is coming from H2O. So 323, that's like 50 degrees Celsius. So 323 Kelvin minus 273 equals 50 degrees Celsius. So in that table, we should look for 50 degrees Celsius and find out what is the vapor pressure of the water at 50 degrees Celsius. And as soon as we have that number, we can do the subtraction. So it's 92.6. It's 92.6. So total pressure is going to be whatever number we find from here plus the 92.6. This is the millimeter mercury. Units must be the same. The pressure that we find from ideal gas law is going to be ATM, and you cannot combine or add ATM and millimeter mercury together. You have to first convert the ATM to millimeter mercury, or convert the 92.6 millimeter mercury to ATM, and then you can add them together. So 0.318, that's the ATM for the pressure coming from H2. We convert that to millimeter mercury, that's 241, plus 92.6, this is coming from the table. You add them together, 330 millimeter mercury. This is the total pressure for oxygen collected. When a reaction is involves gases and the reactant or product side, now before you could have the product as the aqueous solution, or you could have like precipitate. You get the mass of the product, you can find the moles of product, or if it's the aqueous solution, you find the moles, then you could find the concentration. Now, if the product is gas, you often are asked what is the volume of the gas. So from the stoichiometry of the reaction, like when you have balance equation, that would be your step one. Step two is find the number of moles of given, which usually is in the reactant side. But you find the number of moles of given, then you convert that to number of moles of product using the balance equation, or number of moles of what is looking for using the balance equation. Then you answer question. If you remember the 3 steps that I covered before, I say just answer the question. Now, if the question is asking for volume of gas, then you could use the ideal gas law. If it's not STP, and if the condition is STP, just use the molar volume and multiply the number of moles by 22.4 to get to the volume of gas. In this reaction, it says what volume of H2 is needed to make 35.7 grams of methanol. So what is given is the mass of methanol. First, we find the moles of methanol. So we get 35.7 gram of methanol divided by 32.4, which is the number of the molar mass for the methanol. So we can get the moles of methanol. When we have the moles of methanol, then from balance equation, you would say 2 moles of hydrogen for every mole of methanol. So you would say 2 moles of hydrogen. So you look at the blue color, only it says 2 more times the 2 moles of hydrogen over 1 mole of the methanol. And that gives us the number of moles of hydrogen needed. So if we have the number of moles of hydrogen needed, and the condition is not STP. How do we know the condition is not STP? Because STP, temperature should be 273, and the pressure must be 1 atm. So this is not STP. If it's not STP, we are using ideal gas law. If you are using ideal gas law, temperature must be in Kelvin, pressure must be in atm. Number of mole is always number of moles, and we are looking for the V. And V equals nRT over P, pressure in atm. So if you look at this value for the pressure given 738, you want to convert that to atm. You would say 738 times 1 atm over 760. That gives you the pressure in atm. Mole is already, we found the number of moles from stoichiometry of the reaction. So we have the moles of the hydrogen gas, pressure. and the R is the universal constant, and we have the temperature. We can now find the volume. The volume is 66.9 liters under this condition of the temperature and pressure. So basically, the stoichiometry you learned in Unit 5, it's going to be followed the same thing. You start with the balance equation. When you have the balance equation, find enough number of moles of what is given, which in this case is the mass of methanol, which you convert the moles of methanol. Then using the balance equation, find the number of moles of looking for. We found the number of moles of hydrogen, because that's what we are looking for. Then we answer the question. If we have the number of moles of the gas, we can use the ideal gas law to find the volume for the gas. If you have number of moles of gas, you can multiply by molar mass to change that to the mass of the gas. So you can answer the question based on that. Another example, how many grams of H2O form when 1.24 liter of H2 reacts completely with O2 at STP? Okay, so what is given here? We have to have the balance equation. That's step one. Make sure you have the balance equation, step one. And step two, find the moles of given. What is given is the hydrogen. So we have the hydrogen, that's given. But what is given is the volume of the H2, not the moles of H2. We need to find the moles of H2. Because it says STP, and 1 mole of H2 gas is 22.4 liters of the H2. So we can change that to number of moles by dividing by 22.4, or we say 1.24 times the 1 mole over 22.4. This would give us the moles of H2. This was step two. So this is your step two, making sure that you have the moles of given. Then you use the balance equation and you do the next step. You convert the moles of given to moles of looking for. What is looking for is water. And from balance equation, every 2 moles of water is produced for 2, if you use 2 moles of hydrogen. So you just convert the moles of H2 to moles of water. Then if we have the moles of looking for, you answer the question. The question is asking how many grams of H2O. So with the grams of H2O, you have the moles of H2O, you multiply by molar mass of H2O to change that to grams of H2O, and that answers the question. Okay. Another example, so this hopefully you get to, you understand how it works. It's very similar to stoichiometry. The only difference is that in this case, you are using indirect information to find the moles of gas. Sometimes the volume is given, sometimes the mass is given, sometimes, it depends on the information that is given. So you find the moles of the gas. What volume of O2 at this pressure and temperature is generated if 10 grams of mercury 2 oxide is thermolysis? That means it's heated up to decompose to mercury and the oxygen. So what you need is the moles of given. So when you change the mass of given to moles of given by dividing by the molar mass, you have the moles of given. Then use the balance equation to change the moles of the oxygen. So you basically divide by 2, because 2 moles of mercury oxide would give 1 mole of oxygen. When you have the number of moles of oxygen, then you use the ideal gas law to find the volume, because you have the moles, you have the pressure, you have temperature, you have three items, you can find the volume. And the solution for that problem is given here. So we already have the mass of the HGO. We convert that to moles using the molar mass, and then use the balance equation and multiply by this factor, and say for every 2 moles of HGO, you get 1 mole of oxygen. That would give us the moles of oxygen. So we have the moles of oxygen. Since we have moles of oxygen, we have, so this is the N, R is given always. The T, it was provided in Kelvin. And then the pressure, since it's ATM, you don't have to change it. You just use it directly. You could find the liter of oxygen produced. Other topics covered is properties of gases. Gases, they have low density and they can mix with other gases and form homogeneous solutions. They are transparent, they are compressible. And the kinetic molecular theory, particles of the gas are constantly moving. The attraction between the gas molecules is negligible, especially like if the gas is ideal, there's no attraction between them. If they collide or they hit each other, that collision is going to be elastic. That means there's no transfer of energy, and each one would change direction and continue moving. Okay, so when they hit another particle or container, they do not stick, but they bounce off and continue moving to another direction. One other topic is the law of effusion. The effusion is if you have the effusion, meaning that is like the process which collision of molecules escapes through a small hole into the vacuum. This is called effusion. The process that collection of the molecules spreading out from high concentration to low concentration, this is called diffusion. In both effusion and diffusion, molecules of the gas is going to move around. They're going to move, and the speed or velocity of this moving, it depends on the molecular weight or molar mass of the gas. The rate of both effusion and diffusion is inversely proportional to the molar mass. So we have here two formulas. One is rate of effusion, okay? Rate of effusion of gas A over rate of effusion of gas B is inversely proportional to square root of the molar masses. So don't forget this square root, and make sure that if rate B is down, molar mass of gas B would be up, inversely proportional. So this is one of the formulas that we are using. Real gas, basically what real gas means that they are going to the molar volume, they're going to occupy the molar volume. But if it's not a real gas, it's going to deviate from that, is going to take less volume or occupy less volume. So the pressure cause also is going to be lower because there is attraction between the molecules of the gas. Between the gas molecules, again, based on the kinetic molecular theory, there's a lot of space between the gas molecules. That's why we said they are compressible. The kinetic energy of the gases is directly proportional to their temperature. The higher the temperature, they are going to move faster. So if you look at this diagram, at the there are, one of the factor is the molar mass. The higher the molar mass, the lower the velocity. So the higher the molar mass, lower the velocity is going to be. And for hydrogen, which is the lightest gas, is going to have the highest velocity. The other factor that affects the movement of the, or velocity of the gas molecules, is the temperature. The higher the temperature, the higher the velocity, basically greater kinetic energy. We did talk about the difference between effusion and diffusion, but both of them is depends on the molar mass of the gas. And this diagram shows the definition for effusion, because the molecules are going through a opening or small hole, and the smaller the molecule, the faster can escape through that. So this formula can be calculated, can be used to calculate like molar mass or the rate of diffusion. This is a ratio. Both of them are ratio. So you can use the ratio to calculate the missing item. So basically you have rate of A, B, or if you have the ratio, that means you have both of them. So if you have the ratio, you can, and you have the molar mass for A, you can calculate the molar mass for B. The difference between ideal gas and real gases is that ideal gases, there is no attraction between the gas molecules. So gas molecules do not take up any space based on the kinetic molecular theory. At low temperature and high pressure, these assumptions are not valid. So if the temperature is low and pressure is high, the gas is going to behave like a real gas, and they will actually occupy some space. So deviation, if you look at this deviation of the ideal gas, the higher the molar mass, is more deviation you see hydrogen, lighter gas, has lowest difference, okay? Helium and hydrogen. And then when you look at the chlorine, it has greater deviation. So there's a factor of like a van der Waals constant that can be used for the volume. This is like for molecular volume, and it can be added to the ideal gas law. So you have some constant that it depends on the gas, and these values are like they depend on the type of gas or the molecular formula for the gas, and it can be given numbers. You don't have to memorize those numbers. The pressure also, when you calculate the pressure, you have to use this alpha. Again, it depends on the type of gas, and this is another van der Waals constant that is the modification to the ideal gas law. You're not going to get too many calculations based on this, but understand that if you have ideal gas law, or if the gas is at a high temperature and low pressure, you don't have to use this constant, the van der Waals constants, but at low temperature and high pressure, these constants is going to be applied for both pressure and volume, and the value for N and the A is going to be given to. It will be provided. So the reason for that, for those deviation, is that the real gases or gas molecules, they attract each other. So molar volume of the real gases is going to be smaller than the predicted by the ideal gas at low temperature. So these values of A and B, these are the values that would be provided. You don't have to memorize it. Just know that there is some deviation for the pressure and for the volume when the gas is not ideal gas. Okay. When the gas is not ideal gas, there is some deviation based on the constants that is used and provided by the table for the van der Waals constants. Okay, that concludes the chapter.